The strangest thing about the universe is not that it is dark. It is that the part we call dark appears to be holding the bright part together. Look up on a clear night and the mind makes a quiet mistake. It sees stars, a moon, a river of light if the sky is clean enough, and it feels as if the universe has revealed itself. The visible universe seems generous. It gives us points of fire, dusty bands, pale galaxies caught in long exposures, the afterglow of distant explosions arriving long after the dead star has vanished. But that light is not the universe. It is evidence left on the surface. The universe we can see is the small fraction willing to announce itself. It burns, reflects, absorbs, scatters, glows. It leaves fingerprints in telescopes. It can be separated by wavelength, stretched into spectra, measured by temperature, mapped by brightness. It gives science something to hold. And behind it, or through it, or around it, there is something else. Not a monster, not a secret chamber, not a force hiding with intention. Something quieter, colder, and more humiliating than that. The universe behaves as if most of what matters is not made of the stuff that shines. This is where the word terrifying has to be handled carefully. The terror is not that scientists found a cosmic weapon pointed at Earth. It is not that someone opened a forbidden door. It is not even that the universe is strange. Strangeness is almost a requirement at this scale. The terror is that the ordinary picture is wrong in a very specific way. The stars are real. The galaxies are real. The gas clouds are real. The planets, the dust, the comets, the ice, the iron in your blood, the calcium in your bones, all of that belongs to the same visible family of matter. It is the family that can make chemistry, bodies, oceans, atmospheres, rust, breath, memory, and fire. But when scientists count the universe by its behavior, not by its glow, that family becomes small. Painfully small. The atoms that make everything familiar are not the main weight of reality. Almost everything human beings have ever touched, feared, loved, built, eaten, buried, worshipped, and named belongs to the rare part. That is not poetry. It is the shape of the measurements. A telescope does not only collect beauty, it collects betrayal. It shows galaxies turning in ways their visible stars cannot explain. It shows light from distant objects bending around regions where not enough luminous matter exists. It shows clusters behaving as if invisible mass has stayed behind after ordinary gas was stripped away. It shows the early universe carrying patterns that make more sense if unseen matter was already helping gravity gather the first structures. The more carefully the universe is measured, the less the visible universe is allowed to be the whole story. That is the first wound in the title. The secret is not hidden because scientists are careless. It is hidden because light is not the same thing as existence. Light is only one way matter confesses. Most of human intuition was built in a world where that distinction almost never matters. In daily life, if something matters physically, it usually announces itself somehow. A wall blocks you, a stove burns you, water wets your skin, a storm presses against the windows. Even invisible things reveal themselves quickly. Air fills the lungs, wind moves the trees, heat bends the air above asphalt. We grew up inside a scale where presence is usually obvious. The cosmos does not owe us that convenience. Out there, something can shape the motion of a galaxy for billions of years without shining, burning, reflecting, or touching a detector in the way ordinary matter does. Something can be spread through a halo larger than the bright spiral it holds, and the only sign of its presence is that the spiral has not torn itself open. It is a kind of silence with gravity. That silence is why the night sky is misleading. The sky looks like a display of objects. Stars here, planets there, a galaxy in a telescope, a nebula blooming like smoke in long exposure. But the deeper story is written in their motions, in their curves, in the way light travels past them, in the difference between what should happen if visible matter were enough, and what actually happens. The universe is not telling us its secret in light. It is telling us in refusal. A galaxy refuses to rotate the way it should. A cluster refuses to weigh what its brightness says it should weigh. The expansion of space refuses to slow down the way gravity once seemed to demand. Measurements from the early universe and the nearby universe refuse to sit perfectly on top of each other. Not wildly, not uselessly, but enough to leave a pressure mark in the equations. The disturbing part is how controlled the problem is. This is not ignorance in the crude sense. Scientists are not standing in front of the sky with no tools and no map. The modern universe has been measured with a precision that would have seemed almost indecent to earlier astronomers. Telescopes orbit above the atmosphere. Detectors count photons that have crossed billions of years. Spacecraft and observatories divide light into chemical signatures. Microwave maps preserve the ancient warmth of the young cosmos, with tiny variations spread across the whole sky. The mystery survived all of that. It did not shrink because the instruments were weak. In some ways, it became sharper because the instruments became strong. That is a different kind of fear. Not the fear of darkness because nothing is known. The fear of darkness after the lights have been turned on. The body is made of ordinary matter. So is the eye looking through the telescope. So is the mirror of the telescope, the mountain under the observatory, the rocket that lifted instruments above Earth, the paper where equations were first scratched into form. Science is being done by the rare fraction, using tools made from the rare fraction, trying to understand the majority it cannot touch directly. There is a low hum inside that thought. The universe has allowed a little island of visible matter to become conscious enough to notice that it is not the main material. That does not make the island meaningless. It makes it stranger. A galaxy becomes less like a pinwheel of stars and more like a lantern suspended inside an unseen scaffold. The Milky Way is no longer just a river of suns. It is a bright organ inside a dark halo. The halo does not glow for us. It does not make constellations. It does not enter mythology. No ancient shepherd looked up and named its outline. But without it, the story of the galaxy may not hold together. That is the first descent, from light to motion, from appearance to weight, from the visible to the gravitational. And once that descent begins, the universe becomes harder to look at casually. Because every familiar image begins to carry a second image inside it. A spiral galaxy is no longer only a spiral galaxy. It is a visible swirl embedded in a larger, invisible mass. A cluster is no longer only a gathering of luminous islands. It is a gravitational field with bright pieces caught inside it. Empty space is no longer simply empty. It may be crossed by forces, shaped by expansion, structured by things that neither eyes nor cameras can see directly. The secret is not that the universe is hiding in the darkness. The secret is that darkness may have been part of the architecture from the beginning. A galaxy looks peaceful because distance removes the violence from it. From far away, a spiral galaxy can seem almost gentle. A glowing centre, arms loosening outward, blue knots where new stars are forming, dust lanes cutting soft shadows through the light. It has the feeling of something slowly turning in a dark room, enormous but composed, like a wheel that has forgotten it is moving. That beauty depends on ignorance. If you could stand outside a galaxy and watch it for long enough, the softness would disappear. Every star would be in motion, every cloud would be falling around the centre. The whole bright system would be rotating, not like a painted disk, but like a swarm held in a gravitational argument. Gravity gives a galaxy its grammar. Near the centre, where more visible mass is concentrated, stars should move under a stronger pull. Farther out, where the luminous material thins, stars should feel less of that pull. The simple expectation is not difficult to grasp. In the solar system, Mercury moves faster than Earth, and Earth moves faster than Neptune, because the Sun's gravity weakens with distance. Farther objects take longer, slower paths. So when astronomers measured spiral galaxies, they expected the outer stars and gas to behave with that same fading obedience. They did not. The outer regions of many galaxies move too fast. Not a little too fast in a way that can be waved away by a poetic description. Fast enough that the visible matter alone does not appear capable of holding them in those orbits. The stars near the outskirts should behave like dancers at the edge of a loose crowd, barely held by the center, moving more slowly as the light thins. Instead, the rotation curves flatten. The outer material keeps moving at speeds that say, mathematically, that more gravity is present than the light can account for. This is one of the cleanest ways the visible universe betrays itself. A rotation curve is not dramatic to look at. No thunder, no cinematic crack in space, just a line that should fall and does not fall enough. But inside that line is a galaxy refusing to come apart. If the only mass in a spiral galaxy were the stars, gas, dust, and other ordinary matter we can trace, then the outer regions would be moving with an uncomfortable freedom. They would not have enough gravitational loyalty to the system. Over cosmic time, the galaxy would not look the way it looks. The bright spiral would be harder to maintain. The outer material would be less securely bound. The strange conclusion is not that the galaxy is breaking. The strange conclusion is that something unseen is helping it remain whole. This is where dark matter stops being an abstract phrase and becomes a physical pressure on the imagination. It is not introduced because scientists enjoy adding invisible things to the universe. It is introduced because the motions are measurable and the visible matter is insufficient. The galaxy is giving two accounts of itself, one account through light, another through gravity. The gravitational account is heavier. Picture the Milky Way, not as the familiar band of stars across the sky, but as a luminous disk buried inside a vast, dark halo. The disk is the part that makes the photographs. The halo is the part that makes the motion make sense. It may stretch far beyond the visible arms, surrounding the galaxy like an unseen atmosphere of mass, not air, not gas in the ordinary sense, but a distribution of matter that does not shine. You do not see the cage. You see the bird still flying inside it. That image is imperfect, because dark matter is not thought to be a solid shell, not bars, not a container with a surface you could touch. But the emotional truth of the image is useful. The visible galaxy is not alone with itself. Its shape and survival are tied to something larger than its light. The first time this becomes clear, the mind wants an easier explanation. Maybe the stars are being miscounted. Maybe there is ordinary matter too dim to see. Maybe cold gas, dead stars, failed stars, black holes, dust, or some hidden population of faint objects is doing the work. Ordinary unseen matter exists. There are dim stars, there are gas clouds, there are compact objects. The universe contains many things that are hard to detect. But the problem does not disappear when the obvious hiding places are searched. The missing gravity behaves too broadly, too consistently, too deeply woven into cosmic structure to be solved by simply stuffing galaxies with faint, ordinary objects. Ordinary matter interacts with light. It absorbs, emits, heats, cools, collides, forms disks, forms stars, leaves chemical traces. The missing component seems to behave differently. It gathers gravitationally, but it does not announce itself electromagnetically in the expected way. A star is noisy in the language of physics. It produces light, it blows particles into space, it changes the gas around it. A cloud of hydrogen can be traced by radio emission. Dust can redden starlight and glow in infrared. Hot gas shines in X-rays. Ordinary matter, even when hidden, tends to leave fingerprints. Dark matter leaves something more like a footprint in snow after the walker has vanished. The footprint is gravity. This is why galaxy rotation became such a powerful doorway into the problem. It turned the invisible into a measured necessity. It did not reveal the substance. It revealed the absence that a substance would have to occupy. It showed that the universe could be read not only by what arrives at the telescope, but by what the telescope proves should be there because everything else is moving as if it is. There is a quiet, bodily way to feel this. Imagine walking in a circle at the edge of a playground, holding a rope tied to a pole at the center. If the rope is strong, You can move quickly and still remain bound to the circle. If the rope is weak or too long, speed becomes dangerous. You begin to pull away. The circle fails. In a galaxy, gravity is the rope. The outer stars are moving as if the rope is stronger than the visible galaxy says it should be. No one has grabbed the rope directly, but the motion continues, star after star, galaxy after galaxy, with the same unsettling implication. Something is contributing gravity without joining the visible performance. That is why the problem is not solved by saying scientists cannot explain it, as if nothing has been understood. Much has been understood. The shape of the ignorance is precise. The ignorance has curves, maps, equations, excluded possibilities, and instruments built specifically to press against its edges. But precision does not remove the unease. Sometimes it deepens it, because a vague mystery can still be comforting. It leaves room for imagination to soften the edges. A precise mystery is different. It stands still under measurement. It lets you walk around it. It lets you rule things out. It becomes less like a fog and more like an object under a sheet. Galaxy rotation did that. It pulled the sheet tight enough to show the outline, not the face underneath. Only the outline. And once galaxies began to show that outline, the visible universe lost its innocence. A spiral galaxy could no longer be treated as a self-contained island of stars. It became a signpost. Its motion pointed beyond its light. Its beauty became evidence of dependence. The arms still glow. The dust still curls. New stars still ignite in blue-white knots. But the real question has shifted. Not what does the galaxy look like? What is holding the light in place? The first mistake is believing that invisible means unmeasurable. A thing does not have to shine to leave a wound in the path of light. It only has to bend space enough for passing light to obey the curve. The universe does not merely hide mass by making it dark. It allows dark mass to reveal itself by distorting what comes from behind it. This is gravitational lensing. The name sounds technical, almost harmless, but the reality is stranger. A massive object can curve space-time around itself, and light crossing that curved region does not travel through flat emptiness. It follows the geometry. Nothing has to touch the light. No hand reaches out, no surface reflects it, no cloud blocks it. The path itself changes. That means a galaxy cluster can become a lens. A region of space filled with mass can magnify, smear, split, and arc the light of galaxies far behind it. In deep astronomical images, this can look almost delicate. Thin blue-white streaks wrapped around a cluster, small distorted crescents, background galaxies stretched like scratches on black glass. They look decorative until you understand what they are. They are measurements of weight. Not weight in the human sense, cosmic weight, gravitational presence. The amount of mass required to bend light by that much, in that direction, into that shape. And again, the universe gives two answers. The light says one thing, the bending says another. If astronomers add up the visible galaxies in a cluster, the hot gas, and the ordinary matter they can detect through optical, radio, infrared, or X-ray observations, they still do not get enough mass to explain the full lensing pattern. The arcs behave as if the cluster is heavier than it looks. This is where darkness becomes architectural. With galaxy rotation, the clue was motion. Stars moving too quickly in outer regions. Gas refusing to slow down where the visible disk thinned. But lensing is colder, almost more elegant. It asks what happens to light crossing a landscape of gravity on its way to us. A photon may leave a background galaxy billions of years ago, cross emptiness, pass near a foreground cluster, bend slightly through the cluster's gravitational field, and finally arrive in a detector near Earth. By the time the photon is captured, the galaxy that emitted it may have changed beyond recognition. Human civilization may have appeared only in the final instant of that journey. Yet the path still carries the imprint of what bent it. A faint arc on a telescope image can be the fossil of an encounter with invisible mass. There is a small sound hidden in that thought, like a relay clicking in a dark observatory. A detector opens. Photons arrive one by one. They seem weightless, almost innocent. But when enough are gathered, when their positions are compared, when the distortions are mapped, they begin to describe a thing they never struck. They describe the shape of missing gravity. The body understands bending before it understands space-time. A road curbs because the ground demands it. A river bends because stone and slope negotiate its path. A thrown ball arcs because gravity pulls it down. We live among curved paths. But light feels different to us. Light seems like the straight thing, the honest thing, the line between eye and star. Gravitational lensing removes that comfort. Even light can be made to confess that space is not empty in the way the eye imagines. The disturbing part is not simply that mass bends light. General relativity prepared science for that. The disturbing part is that the amount and distribution of bending often point beyond the luminous matter. The visible galaxies in a cluster become like lamps hung in a larger invisible room. The lamps show where some matter is, but the lensing tells you the room is much bigger and more heavily furnished than the lamps reveal. Sometimes the evidence becomes sharper when cosmic violence separates the components. In certain cluster collisions, ordinary gas can be slowed, heated, and displaced because ordinary matter interacts with itself. Gas clouds collide, they shock, they glow in X-rays, but the gravitational mass traced by lensing can appear offset from that hot visible gas, aligned more closely with the collisionless components. Such systems suggest the missing mass behaves differently from ordinary matter. It passes through more cleanly. That does not solve dark matter. It does not tell us the particle. It does not hand science a sample in a vial. But it tightens the shape of the problem. The missing mass cannot simply be all the normal gas we fail to see, because the gas is visible in X-rays and behaves like gas. The universe is separating the suspects. This is why the word dark can mislead. It makes dark matter sound like ordinary matter painted black, as if the problem were only a failure of illumination. But the darkness is not just a visual fact. It is a behavioral fact. Dark matter, if the current interpretation is right, does not participate in the electromagnetic conversation the way ordinary matter does. It gathers, but it does not glow. It weighs, but it does not speak. This turns gravitational lensing into one of the most haunting tools in modern astronomy. It allows scientists to map something by watching how everything behind it is subtly damaged. The background universe becomes graph paper. Distant galaxies become test lines. Their distortions reveal the invisible field in front of them. A cluster image is therefore not just a photograph. It is an interrogation. The bright galaxies in the foreground are only part of the testimony. The stretched arcs behind them are another part. The X-ray gas is another. The calculated mass map is another. Each layer asks whether the same matter can explain all the observations. Very often, ordinary matter cannot carry the whole burden. So, the invisible returns. Not as superstition, not as fantasy, not as a gap where anything can be inserted. As a constraint. Dark matter is not allowed to be whatever the imagination wants. It must fit galaxy rotation. It must fit cluster lensing. It must fit the cosmic microwave background. It must fit the formation of large-scale structure. It must avoid leaving ordinary light signatures where they have not been seen. It must be abundant enough to shape galaxies, but elusive enough to evade direct detection so far. That combination is not comforting. It is almost humiliating in its precision. Human beings learned to trust light because, for most of our history, light was the boundary of knowledge. Firelight at the edge of a cave, starlight for navigation, sunlight for seasons, a glowing screen full of data from an orbiting telescope. To know was to illuminate. But the universe keeps teaching a colder lesson. Sometimes understanding begins when illumination fails. A gravitational lens is a kind of dark mirror. It does not show the hidden mass directly, It shows what hidden mass has done to something else. A footprint is not a foot. A shadow is not a body. A bent beam is not a hand. Yet all of them can be evidence. The more lensing maps improve, the more the bright universe becomes surrounded by an invisible anatomy. Filaments, halos, dense knots around clusters, wide structures that guide how galaxies assemble and where matter falls. The cosmos begins to resemble not a scattering of luminous islands, but a dark framework with fire caught in its joints. And then the original question changes again. It is no longer enough to ask what holds a galaxy together. The harder question is what holds the map together. If invisible mass can bend light, shape clusters, guide galaxies, and leave its signature across enormous distances, then darkness is not the absence of structure. Darkness may be the structure through which the light learned where to go. Once the invisible mass appears in a galaxy, the mind tries to keep it local. That is a defensive instinct. It is easier to imagine that something strange has happened to a few rotating disks than to accept that the architecture of the whole universe may depend on what cannot be seen. A galaxy is already remote enough. A cluster is already large enough. The imagination can place the mystery there, at a distance, and hope the rest of reality remains ordinary. But dark matter does not stay politely inside one example. It appears wherever gravity has been patient enough to build structure. The universe is not arranged randomly. Galaxies are not sprinkled through space like dust shaken from a cloth. On the largest maps, they gather into filaments, sheets, knots, and enormous empty regions. There are walls of galaxies stretching across hundreds of millions of light years. There are clusters and superclusters where gravity has pulled luminous matter into crowded cities. There are voids so large that a galaxy inside one would look out and see a much lonelier sky. The visible universe has a texture, and that texture needed help forming. Ordinary matter alone has a problem in the early universe. It interacts with light. In the young cosmos, before atoms formed, ordinary matter was tangled with radiation in a hot plasma. Photons pushed against it. Pressure waves moved through it. It could not simply begin collapsing into deep gravitational wells without being resisted by the intense radiation field around it. Dark matter, as the standard picture describes it, had a different role. Because it did not interact with light in the same way, it could begin gathering gravitationally without being dragged through the same bright resistance. It could create the invisible wells into which ordinary matter later fell. The stars and galaxies we see would then be late arrivals, fire settling into dark scaffolding that was already there. That is an unsettling reversal. The light did not build the stage. The stage was waiting for the light. To feel the scale of that, imagine a city seen from the air at night. Roads appear as threads of headlights. Buildings become grids of lit windows. The whole place seems to be made of illumination. But daylight would reveal something the night view concealed. Foundations, pipes, tunnels, concrete, cables, drainage, the buried systems that make the lights possible. The cosmic web is like that, except the hidden infrastructure is not beneath the lights. It is around them, between them, and in some sense before them. Galaxies mark the places where ordinary matter became visible enough to announce the underlying pattern. They are the lamps, not the wiring. And the wiring, if dark matter is the right explanation, is spread across distances so large that a human lifetime becomes useless as a measuring tool. 100 million light-years is not a distance the body can hold. It is not a road. It is not a voyage. It is not even a horizon. Light itself, moving fast enough to circle Earth more than 7 times in a second, needs 100 million years to cross it. That means a structure of that size is not merely far away. It is older in its own visibility than species, climates, mountains, and memory. When astronomers map galaxy surveys, they are not seeing the universe as it is in one simple now. They are seeing a time-layered skeleton. Nearer galaxies appear more recent. Farther ones appear younger, because their light began the journey long before it arrived. The map is spatial and historical at once. A low electronic hum fills the control room. A screen shows points of light converted into positions, redshifts, distance estimates. What looks like data becomes a web. What looks like a web becomes a fossil of gravity's slow preference. Matter has not gathered everywhere equally. It has gathered where the invisible gradients told it to gather. This is why dark matter is not just an explanation for one failure in one measurement. It is part of a larger coherence. Galaxy rotation curves point toward extra mass. Lensing maps point toward extra mass. Cluster dynamics point toward extra mass. The cosmic microwave background points toward a universe whose structure grows properly only if a non-luminous matter component is included. Large-scale galaxy distributions fit more naturally when dark matter helps seed and shape the cosmic web. Each line of evidence has its own instruments, its own errors, its own assumptions. The unease comes from their convergence. A weak idea survives by avoiding tests. Dark matter has survived because many different tests keep returning to something like the same need. Not the same complete answer, not the particle, not the final mechanism, but the same gravitational absence outlined from different directions. This does not mean scientists know what dark matter is. It means the universe keeps behaving as if the visible inventory is missing a major category. There is a deep difference between those sentences. One is certainty about substance, the other is confidence in a problem. Good science often lives in that difficult middle state, where the evidence is strong enough to demand an explanation, but not yet generous enough to reveal the thing itself. That middle state can last a long time. It can outlive careers. It can build instruments, consume conferences, shape theories, rule out candidates, and still leave the central object untouched. For the public, this can sound like failure. For science, it is more complicated. A well-defined failure can be progress. It means the unknown has boundaries. It means the next wrong answer has fewer places to hide. Dark matter has been cornered many times without being caught. It has been modelled as a halo around galaxies, as a component in cosmological simulations, as a driver of structure formation, as a possible particle beyond the known roster. It has been searched for in underground detectors shielded from noise, in particle accelerators, in astrophysical signals, in the faint possibility that rare collisions might leave a trace. Each effort pushes against the same silence from a different side. The silence remains. But silence here is not emptiness. It is a limit in how ordinary matter can interrogate something that may barely interact with ordinary matter except through gravity. If dark matter passes through planets, detectors, bodies and walls almost without noticing them, then every experiment is like trying to hear a whisper from something that almost never touches the air. That image is dangerous if taken too literally, but useful if held lightly. Because the point is not that dark matter is ghostly in a supernatural sense. The point is that interaction is the price of detection. To observe something directly, it has to exchange something with the detector: light, heat, charge, momentum, a decay product, some trace that ordinary matter can register. Gravity registers everywhere. But gravity is weak, diffuse, and difficult to isolate at particle scales. On cosmic scales, it becomes magnificent. It shapes galaxies. It bends light. It gathers clusters. On the scale of a laboratory encounter, it becomes almost impossibly subtle. So the universe gives us dark matter in two cruelly mismatched ways. Enormous enough to shape the cosmic web. Too elusive to hold in a human-made trap. That mismatch is part of what makes the subject feel so strange. If something is powerful enough to guide galaxies, the body expects it to feel powerful nearby. It should roar, burn, push, poison, strike. But power at cosmic scale is not always violence at human scale. A tide can move an ocean while a cup of water stays quiet in your hand. Gravity can steer a planet for billions of years and still feel like simple weight under your feet. Dark matter's influence may be everywhere without becoming an experience. You do not feel the halo of the Milky Way passing through the room. You do not hear it in the walls. It does not darken the window. It does not chill the skin. It is not waiting in the corner with intention. And yet, if the standard picture is right, the room, the planet, the sun, and every visible star in the galaxy are moving inside its larger gravitational presence. This is where the architecture becomes almost intimate. The hidden scaffolding is not far away only. It is not confined to remote clusters and elegant telescope images. Earth orbits inside the Milky Way. The Milky Way sits inside a dark halo. The halo belongs to a larger cosmic web. The atoms in a human body are part of the rare luminous fraction carried along within a structure they did not build and cannot fully inspect. The bright universe begins to feel less like a kingdom and more like a thin frost on an invisible machine. That machine is not a metaphor for design. It has no known intention, no engineer, no purpose written into it. But it has order. It has consequence. It has a history written in gravity. It decides where galaxies can grow, where clusters become dense, where voids remain poor, where light gathers and where it never had enough material to ignite. A deep survey of the universe is therefore not merely a catalogue of galaxies. It is a map of obedience. Each galaxy marks a place where matter followed the curvature of a larger field. Each filament marks a path where gravity won slowly over expansion. Each void marks a region where matter was sparse enough that time did not fill it with fire. The secret has widened again. It is no longer only that galaxies need invisible mass to hold their outer stars. It is that the visible universe may be tracing an invisible structure, the way foam traces the surface of a wave. The foam is real. The light is real. The galaxies are real. But they are not the whole water. And somewhere beneath the glow, the larger current keeps moving. The oldest light in the universe does not look like light anymore. By the time it reaches us, it has been stretched by expansion until its fire has cooled into microwaves. It does not arrive as a blaze. It arrives as a faint background, a low afterglow filling the sky from every direction, colder than any human night and older than every star we can see with the naked eye. This is the cosmic microwave background. It is sometimes called a baby picture of the universe, but that phrase makes it sound softer than it is. It is not a portrait in the sentimental sense. It is a surface of last contact, a record from the time when the universe cooled enough for electrons and nuclei to form neutral atoms, letting light travel freely instead of being scattered again and again through a hot, dense plasma. Before that moment, the universe was opaque. Not dark in the ordinary sense. Too bright, too crowded, too tightly coupled for light to cross freely. Photons were trapped in a glowing fog of charged particles, unable to carry a clean image across distance. Then, as the cosmos expanded and cooled, the fog thinned. Atoms formed, light escaped. And it has been travelling ever since. When instruments map that ancient radiation, they are not seeing galaxies. They are not seeing stars. They are seeing a time before the first stars, before the first planets, before chemistry had built anything that could look back. The map is almost uniform, almost the same temperature everywhere, and that almost is where the entire future hides. Tiny variations. Small differences in density and temperature. Slightly hotter and colder patches, no louder than a whisper in the original fire. Those variations are not decoration, they are the seeds of everything that followed. Regions that were a little denser had a little more gravity. Regions that were less dense became the beginnings of emptier space. Over immense time, gravity amplified the small differences. Matter fell toward matter, gas gathered, stars ignited, galaxies formed, clusters assembled, voids widened. The modern universe was already written in faint unevenness before there were lights to admire. This is where dark matter enters the story from an older direction. Galaxy rotation and gravitational lensing show missing mass in the mature universe. They catch the invisible by watching what galaxies and light are doing now, or what they were doing when their signals began the journey toward Earth. The cosmic microwave background asks a colder question. What ingredients did the universe need before the galaxies existed? The answer is not guessed from a single patch of sky. Satellites and observatories have measured the background radiation with extraordinary care, especially its temperature patterns across the full sky. Those patterns can be compared with models of an expanding universe filled with different proportions of ordinary matter, dark matter, radiation, and dark energy. Change the ingredients, and the pattern changes. The peaks and ripples in the data shift. This is one reason the dark universe cannot be dismissed as a local misunderstanding. The missing component is not only found by watching galaxies today, it is implied by the oldest observable light, by the way the early universe was vibrating before it became transparent. The same hidden category that helps galaxies form also helps the first map of the cosmos make sense. There is something almost unbearable about that continuity. The problem was not added later. It was present in the beginning we can observe. Not the absolute beginning, because science cannot simply look back to time zero and speak with perfect certainty. The microwave background does not show the first instant. It shows the universe hundreds of thousands of years after the hot, dense, early state began expanding. That is ancient beyond ordinary feeling, but not infinite. It is a wall of visibility, not a window through everything. Still, it is far enough back to humble almost any explanation built only from recent structures. Dark matter is not a patch placed over spiral galaxies because their edges move too quickly. It appears in the early pattern from which those galaxies later grew. It is part of the accounting that makes the whole cosmic story cohere across time. A quiet room, a monitor, a full sky oval map coloured in tiny differences. This is one of the least dramatic images ever produced by one of the most dramatic facts. The map does not look frightening. It looks controlled, almost abstract. A mottled surface, red and blue variations, a code written across the sky. But that code says the visible universe was never enough. If ordinary matter had been the only gravitational actor, structure would not have grown in the same way. Radiation pressure in the early plasma would have fought collapse. The timing and scale of the later web would be different. Galaxies would not assemble with the same ease, in the same abundance, into the same kinds of patterns we observe. The dark component gives gravity a head start. It deepens the wells before ordinary matter can fall fully into them. It helps explain why the universe did not remain too smooth, too diffuse, too late in forming the luminous structures that eventually made planets and bodies possible. The unsettling truth is that darkness may have helped make stars possible. Not darkness as evil, not darkness as intention. Darkness as a name for matter that did not shine, but still pulled. The body wants light to be the creative force. We are built around sunlight. Food chains begin with it, eyes evolved for it, days are organized by it. Heat from a star keeps oceans liquid and skin alive. In human terms, light is life's great permission. But cosmology tells a more severe story. Before light could become life, unseen gravity had to prepare places for ordinary matter to gather. Before there were warm planets, there had to be wells. Before there were suns, there had to be collapse. Before collapse could make the first stars efficiently, the young universe needed ingredients that did not behave like ordinary glowing plasma. The visible world depends on the invisible one so deeply that even our idea of beginning has to be corrected. The afterglow of the Big Bang is therefore not merely ancient light. It is a receipt. It preserves the proportions and pressures of a universe that was already dividing itself into what would shine and what would only weigh. It tells us that the bright part had partners from the start, partners whose names are still partly placeholders. Science can reconstruct a great deal from the microwave background. It can estimate the age of the universe within the standard model. It can infer the relative amounts of matter and energy. It can constrain geometry and compare early universe predictions with later structure. It can turn a faint chill across the sky into a history of cosmic growth. And still the central substances remain unnamed. The map is precise. The identity is missing. That combination is what makes the subject difficult to domesticate. A vague claim would be easy to ignore. A precise map with unknown ingredients is harder. It means our ignorance is not floating outside knowledge. It is embedded inside one of the most successful descriptions of the universe ever made. The same model can predict and confess. It can fit the old light with astonishing elegance, and then quietly admit that most of the fitted universe consists of components we do not understand at the deepest physical level. That is not a failure of measurement. It is a revelation of scale. A faint hiss in the microwave sky tells us that ordinary matter was never the main author of structure. Stars are not the first sentence. Galaxies are not the first sentence. Life is not even in the opening paragraph. By the time anything burned, the grammar of gathering had already been written. And when we look at the map after the fire, we are not only seeing where the universe came from, we are seeing how much of its beginning was already hidden from light. There is a strange comfort in a mystery that stays far away. A galaxy can rotate too quickly. A cluster can bend light too strongly. The early universe can carry the fingerprint of missing mass. As long as all of that remains in the sky, the problem can feel almost clean. It belongs to maps, equations, observatories, and old photons. It belongs to distances so large that the body can only surrender. But dark matter does not only ask astronomers to measure the heavens. It asks matter here on Earth to answer. If the Milky Way is embedded in a dark halo, then Earth is moving through that halo. The planet is not outside the mystery, looking at it like a photograph on a wall. It is inside the field being studied. Every laboratory, every detector, every hand adjusting a cable underground is carried through the same unseen population that helps explain the galaxy's rotation. The thought sounds almost intimate. Some dark matter may be passing through the room right now. Not as fog, not as smoke, not as a ghost in the theatrical sense. If the leading ideas are even roughly right, it would pass through ordinary matter with almost no interaction, leaving no chill on skin, no shadow on the floor, no mark in a glass of water. It would not feel like arrival. It would feel like nothing, because feeling is made of interactions, and interactions are exactly what seem to be rare. To detect something directly, a detector must receive a trace. A particle has to collide, scatter, deposit energy, produce a flash, create charge, leave heat, or leave some event that ordinary matter can register. Every instrument is a carefully prepared question, built from atoms, waiting for the universe to answer in the language atoms can understand. Dark matter has not answered clearly. That absence is one of the most important facts in the story. For decades, physicists have built experiments to catch a dark matter particle in the act of touching normal matter. Many of these detectors are placed deep underground, beneath rock, where the noise from cosmic rays is reduced. The setting itself feels like a confession of difficulty. To listen for something almost silent, science has to go under mountains, into shielded rooms where tanks of liquid xenon or other materials wait in the dark for a tiny flash that may never come. A detector underground does not look like a telescope staring into eternity. It looks more like a patient trap. Metal, cables, insulation, sensors, clean rooms, a low mechanical hum, human footsteps softened by protocol. Everything is designed to remove ordinary interference so that an extraordinary whisper, if it happens, will not be lost. Most of the time, nothing happens. Or rather, many things happen, but not the one thing needed. Radioactivity, neutrinos, instrument noise, background events. The ordinary universe keeps making small marks. The experimenters subtract, filter, model, shield, refine, and wait. A candidate event has to survive a long interrogation before it can be trusted. A signal too eagerly believed can become a false discovery. A silence too quickly accepted can hide a weak truth. So the search becomes a discipline of restraint. This is why the missing particle feels different from the missing mass. In the sky, dark matter is enormous. It gathers around galaxies, shapes clusters, helps write the cosmic web. In the laboratory, it becomes almost absurdly elusive. The same thing that may steer stellar cities across hundreds of thousands of light years refuses to produce one unmistakable local touch. A thing large enough to matter cosmically should feel large. That is what intuition says. But intuition was trained by stones, rain, animals, heat, wood, metal, tools, wounds, bodies. It was not trained by a substance whose collective gravity can dominate a galaxy, while each individual encounter with ordinary matter may be nearly impossible to notice. Scale deceives us. Gravity is cumulative. A vast halo can shape the Milky Way because all its mass adds together across immense distance. But one particle crossing one detector may carry only a tiny chance of interacting. Cosmic influence does not guarantee local violence. The ocean can lift a continent's weather and still enter a single cup as silence. That is the cruel elegance of the dark matter search. The universe has given us its gravitational signature in abundance, then withheld the handshake. Theories have tried to supply the missing identity. Weakly interacting massive particles became one famous candidate. Axions became another possibility, lighter and stranger, born from a different theoretical need. Sterile neutrinos, primordial black holes, and other ideas have also been explored, constrained, challenged, revived, or narrowed. But no candidate has become the answer. That does not mean all candidates are equal. Some are more constrained than before. Some once promising hopes have been made smaller by the lack of detection. The unknown is not a shapeless hole anymore. It is a field of possibilities with walls closing in unevenly. The silence has structure. Particle accelerators add another kind of pressure. If dark matter belongs to physics beyond the known roster of particles, perhaps it could be produced in high-energy collisions and inferred from imbalance, from missing energy, from the fact that the visible products do not close the books. Once again, the evidence would be a footprint, not the foot. At every scale, dark matter keeps entering through consequence rather than appearance. Galaxies rotate as if it is there. Light bends as if it is there. The microwave background fits better if it was there early. Detectors wait as if it may touch them. Colliders search for events where it may leave by carrying energy into invisibility. The story is full of doors, and none of them open onto the object itself. There is a temptation then to make the mystery mystical, to turn dark matter into cosmic shadow stuff, to let the name do more work than the evidence. That temptation has to be resisted. Dark matter is not a mood. It is not darkness in the moral or spiritual sense. It is a name for a gravitational problem whose best current explanation may be matter that does not interact with light. A name can be useful and incomplete at the same time. We like names to feel like possession. Once a thing has a label, it seems partly contained. The words become smooth from repetition, and the smoothness can hide the wound underneath. Dark matter sounds almost settled. It is not. The label marks the place where evidence is stronger than identity. It tells us that something with gravitational effect is missing from the visible inventory. It does not tell us what that something is made of, whether it is one particle or a family, whether the answer will come from a detector, an accelerator, an astronomical anomaly, or a revision of the theory used to interpret the evidence. And yet the search itself changes the meaning of the universe. It shows that knowledge is not always a movement from darkness into light. Sometimes knowledge is a movement from vague darkness into measured darkness. The unknown becomes sharper, colder, more constrained. It loses fantasy, but not mystery. Deep underground, a detector keeps waiting. Above it, cities sleep, satellites move through sunlight, and the Milky Way carries everything through its dark halo. The instrument is built from ordinary atoms, surrounded by ordinary rock, monitored by ordinary bodies with ordinary eyes. It waits for the majority of matter to do something almost impossibly small. A tiny flash. A displaced charge. A trace that can survive every test. Until that arrives, the galaxy remains heavier than its light, the cosmic web remains scaffolded by an unseen component, and the particle that may explain it all keeps passing through the story without becoming visible. Not absent. Uncaught. For most of human history, the universe was allowed to have an ending that felt almost understandable. Not comforting exactly, but understandable. Gravity was the great collector. It pulled dust into stars, stars into galaxies, galaxies into clusters. It slowed motion, gathered matter, bent paths inward. Even when the universe was discovered to be expanding, the old intuition remained. Expansion was the thrown stone, gravity was the hand reaching after it. The only question seemed to be whether the stone would slow forever, stop, or someday fall back. The universe could expand forever into coldness, or it could reverse into collapse. Either fate was enormous, but the logic was clean. Gravity pulls, expansion resists. Measure the contents carefully enough, and the ending might be calculated like the arc of an object in flight. Then the arc changed. Distant exploding stars, used as cosmic distance markers, appeared dimmer than expected, in a way that pointed toward a shocking possibility. The expansion of the universe was not merely continuing, it was speeding up. Space itself, on the largest scales, seemed to be stretching faster with time. This did not feel like a small adjustment. It felt like discovering that the stone, instead of slowing as it climbed, had begun to accelerate away from the hand. The observations were built from Type 1a supernovae, stellar explosions whose brightness can be used, carefully and with corrections, to estimate distance. Astronomers compared how bright these events appeared with how much their light had been stretched by cosmic expansion. The results suggested that the universe had expanded more slowly in the past than it does now. Something had changed the expected story. Gravity had not vanished. Matter still gathered. Galaxies still held their stars. Clusters still formed. The cosmic web still carried the deep memory of attraction. But on the largest scales, across the widest separations, another effect seemed to be winning. The name given to that effect was dark energy. It is a dangerous name because it sounds like discovery in a bottle. Dark energy. 2 words, almost too smooth, as if the universe had confessed its mechanism and science had simply written it down. But the name is not the answer. It is the bruise where the answer should be. Dark energy refers to whatever is driving, or is associated with, the observed accelerated expansion of the universe. In the simplest version of the standard cosmological model, it behaves like a cosmological constant, an energy of space itself, steady in density even as space expands. That idea has a strange consequence. As the universe grows, matter becomes more diluted. But if the energy density of empty space remains constant, then more space means more total dark energy in the expanding volume. The emptiness does not thin out in the same way. This is difficult to feel because the body has no honest experience of space as an active ingredient. Empty space, to us, means room, a corridor, the gap between walls, the distance between one hand and another. We treat emptiness as absence because, at human scale, absence usually behaves politely. Cosmic emptiness is not so polite. If dark energy is something like a property of space, then the void is not merely a background in which the universe happens. It is part of the budget. It enters the equations. It changes the fate of galaxies, not by pushing them like wind against sails, but by altering the large-scale behavior of expansion itself. The image is almost impossible to make physical. No one stands at the edge of a galaxy and feels dark energy as a breeze. No instrument has dipped a cup into empty space and brought back the substance. There is no glowing fluid between clusters, no visible pressure wave moving through the dark. There is only the pattern. Distant supernovae, the cosmic microwave background, large-scale structure, baryon acoustic oscillations, those ancient ripples in the distribution of matter, multiple ways of reading the universe's history, all forced to account for a period in which expansion accelerated. Once again, the evidence is not a direct sighting. It is a demand placed on explanation. Stand on Earth at night, and the expansion is completely hidden from the senses. The ground is still. The air moves for local reasons. The moon crosses the sky because Earth turns. The stars seem fixed enough that old constellations survive human generations. Nothing in the body reports that the universe is stretching. But far beyond the gravitational grip of the local group, the deep pattern changes. Galaxies not bound to us are being carried away by the expansion of space. The more distant they are, the faster that recession appears, not because they are flying through space like shrapnel from a central explosion, but because the space between large-scale structures is expanding. Dark energy makes that separation more severe with time. The old fear was collapse, a universe that might someday fall inward, heating, crushing, undoing its expansion in a final return. There was something almost mythic about that possibility, a cosmic inhalation after the exhale. The newer fear is quieter. Not fire, distance. If accelerated expansion continues in the simplest way, distant galaxies will become increasingly unreachable, not only by spacecraft, which were always hopelessly slow on that scale, but eventually by observation. Their light will be stretched, reddened, weakened. Future observers in a far older universe may find a sky emptied of evidence that other galaxies ever existed beyond their bound neighborhood. The universe would not end with a scream. It would lose addresses. This is the bodily translation of dark energy. Imagine standing on a shoreline while every other shore recedes faster each century, not because the water rises between you, but because distance itself is being manufactured. A signal sent outward has farther to cross. A reply becomes less likely. A galaxy that was once visible fades beyond practical reach. The map does not burn. It becomes irrelevant. The terrifying part is not immediate danger. The terrifying part is that separation may be built into the future. Dark matter pulled the mind toward hidden weight. Dark energy pulls it toward hidden fate. One shapes where galaxies gather. The other shapes how the largest distances grow. One helps explain the architecture of cosmic structure. The other helps decide whether that architecture remains mutually visible. Together, they make ordinary matter feel even more provisional. Stars burn in the narrow permissions between invisible gravity and accelerating emptiness. Galaxies shine inside halos, while the space between unbound galaxies obeys an expansion driven by something not yet understood. The visible universe becomes not a kingdom, not even a stable map, but a temporary arrangement of light inside two deeper unknowns. One unknown helps things come together. The other pulls the unbound apart. And science is caught between them, measuring with increasing precision a universe whose most powerful ingredients still refuse to become familiar. That is why dark energy feels colder than dark matter in a certain way. Dark matter at least gathers. It participates in structure. It gives galaxies a hidden mass, clusters a deeper field, the cosmic web a scaffolding. It is mysterious, but it is involved in making things. Dark energy does not seem to build in that intimate sense. It separates. It says that beyond a certain scale, no matter how bright the galaxies are, no matter how many stars they contain, no matter how much history unfolds inside them, the space between them can become the dominant fact. A quiet telescope can still catch their ancient light for now. Detectors can still measure redshift, brightness, pattern, distance. The old photons still arrive, thin and tired, carrying messages from structures that expansion is already carrying farther away. But the message inside dark energy is not simply that the universe is large. It is that the largeness may be increasing faster than gravity can make meaningful on every scale. The expansion that should have slowed did not obey the old expectation. It turned the emptiness between galaxies into a physical question. It made the fate of everything luminous depend on something no one has touched, isolated, or understood. And after dark matter taught us that light is not the same as mass, dark energy teaches an even quieter lesson. Distance is not the same as emptiness. Dark energy is one of those names that makes the unknown sound more owned than it is. The phrase has weight. It has rhythm. It feels almost like a substance, something that could be coloured in a diagram, then placed beside dark matter and ordinary matter, as if all three were equally understood. Ordinary matter makes stars. Dark matter makes halos. dark energy makes expansion accelerate. Clean, useful, dangerous. Because a clean sentence can hide the fact that the deepest part remains open. Dark energy is not dark in the same way dark matter is dark. Dark matter is called dark because it does not emit or absorb light in the ordinary detectable way, while still acting gravitationally like matter. Dark energy is stranger. It is not a hidden population of particles moving through galaxies, at least not in the simple picture. It is the name placed over the accelerated expansion of the universe. The name does not tell us what it is. It tells us where the explanation is missing. That matters because language can domesticate fear too quickly. Once a mystery has a label, the mind relaxes. Dark energy becomes a fact in a textbook, a slice in a cosmic pie chart, a term repeated so often that its original shock fades. But the original shock is still there. The universe appears to be accelerating in its expansion, and the cause is not known. Hold that without smoothing it. Not just expanding, accelerating. Not just distant galaxies moving away. The large-scale fabric between unbound structures changing in a way that makes separation grow more aggressively over time. Not from an explosion into pre-existing space, but from space itself, expanding according to rules that still contain an unidentified component. That is why dark energy is less like an object and more like a confession. It is a technical confession, not a helpless one. Scientists can measure effects associated with it. They can compare models against supernova distances, the cosmic microwave background, galaxy clustering, weak lensing, and the growth of cosmic structure. Surveys can ask whether its influence has changed over time or stayed consistent with a cosmological constant. But measuring the shadow of a cause is not the same as holding the cause. A cosmological constant is the simplest explanation. In that picture, dark energy behaves like an energy density inherent to space itself, steady as the universe expands. Empty space would not be merely empty. It would have a property that helps determine cosmic fate. The room between galaxies would count. Not as dust, not as gas, as something built into the accounting of space. This is where ordinary intuition fails again. We're used to thinking of emptiness as a lack. If a room is empty, there is nothing in it. If a cup is empty, it contains no water. Emptiness is passive, a permission for other things to exist. Cosmology does not let emptiness remain that innocent. On the largest scales, what looks like absence may have behavior. It may have consequences. It may decide whether the far future keeps galaxies in mutual view or slowly removes them from one another's observable universe. The void is not just the stage. It may be part of the plot. There is a quiet horror in that, but not the loud kind. No alarm sounds when space expands. No border tears open. A galaxy continues forming stars. A telescope mirror opens above Earth and collects a few ancient photons. The change is too large and too slow for the body. It happens across baselines so immense that ordinary sensation has no organ for it. And yet it changes everything that can remain connected. Imagine two small islands in a dark sea. At first they are distant but visible. A lamp on one shore can still be seen from the other. Then the sea itself begins to widen. Not the islands sailing apart through water, but the water becoming more water between them. The lamp still burns. The eye still waits. A universe with persistent accelerated expansion develops horizons. There are regions from which light emitted now will never reach us, because the expansion of space prevents the signal from closing the distance. The universe may contain places that are real, structured, full of stars, perhaps full of histories, and yet permanently unavailable to any future observer here. Existence and accessibility separate. That is colder than emptiness. Dark energy is therefore not merely a problem about speed, it is a problem about relationship. What can influence what? What can be seen? What can ever be reached? What parts of the cosmic record will remain available, and what parts are being slowly carried out of the archive? The universe becomes not only a place where things exist, but a place where existence can retreat beyond contact. If dark matter made the visible universe dependent on hidden scaffolding, dark energy makes the visible universe temporary as a shared view. The galaxies we observe at extreme distances are not just far away. They are old messages from regions whose future relationship with us may already be sealed by expansion. A telescope, in that sense, becomes a machine for catching departures. The photons arrive with almost no drama. They strike a detector. They become data. A redshift is measured. A point enters a catalogue. But inside the data is a slow severing. The universe is large enough that seeing something does not mean sharing a future with it. That is the kind of terror dark energy earns. Not panic. Dispossession. It takes the night sky, which already made human beings feel small, and makes smallness more exact. We are not simply tiny in a vast universe. We are tiny inside a changing visibility. The map available to any civilization is not guaranteed to remain open. The cosmic evidence itself may depend on when the observers appear. Arrive too late, and the universe may look poorer than it was. A far future astronomer in an isolated galaxy group might not see the same cosmic abundance we see. The evidence for expansion, for other galaxies beyond the local bound structure, for the wider cosmic web, could be harder to recover. The universe would still have a history, but much of the witness would be gone from view. That possibility turns dark energy into an attack on certainty. Not because it makes science weaker, but because it shows how much science depends on timing. We live in an era when the ancient microwave afterglow can still be measured, when distant galaxies still send usable light, when large-scale structure can still be mapped. Knowledge is not only intelligence. It is also cosmic luck. The fact that we can ask these questions now is part of the answer's fragility. The universe is not obligated to remain legible forever. It does not preserve every clue for every future mind. It allows windows, and windows close. This is why the name dark energy should never feel like a completed explanation. It is a placeholder, placed with discipline over one of the deepest gaps in physics. It may turn out to be the cosmological constant. It may point toward a dynamic field. It may expose something incomplete in how gravity is understood. The honest position is not ignorance without structure. It is structured ignorance under measurement. At each step, the universe gives enough to calculate and withholds enough to humble. The word secret is imperfect because it suggests intention. But if the word means a truth hidden behind appearance, then dark energy may be one of the largest secrets ever named. The appearance is empty space. The hidden truth is that emptiness may determine whether the universe remains mutually visible or slowly disappears from itself. A faint signal crosses billions of years and lands in a detector. For a moment, contact still happens. Then the expansion continues. There is a special kind of fracture that appears only when two careful measurements both refuse to be dismissed. A bad measurement is easy to fear for a moment, then discard. A calibration error can be found, an assumption can be corrected. Science has many ways to protect itself from being fooled by one instrument, one team, one beautiful result that arrives too cleanly. The harder problem begins when different methods, built on different evidence, point toward answers that are close enough to belong to the same universe, but not close enough to fully agree. That is the Hubble tension. The name sounds almost modest. Tension. Not crisis, not collapse, not proof that everything is broken. It is a careful word for a stubborn mismatch in the measured expansion rate of the universe. But careful words can hold deep pressure. The expansion rate is tied to the age of the universe, its contents, its history, and the model used to connect the early cosmos to the present one. The problem begins with a ruler. Not a wooden ruler, but a ladder of distances built across space. To know how fast the universe is expanding now, scientists need to know how far away things are and how fast they appear to be receding. Nearby objects can be measured one way. Further objects require another. Each rung must be tied to the last with enough care that the ladder does not bend under its own ambition. Cepheid variable stars help calibrate distances. Type 1a supernovae extend the reach farther out. Redshifts reveal how much the light has been stretched. Together, these methods allow astronomers to estimate the present expansion rate from the relatively nearby universe. This is the local route. It is built from stars and explosions. There is another route that begins almost at the opposite end of time. The cosmic microwave background carries the pattern of the early universe. If scientists use that ancient pattern within the standard cosmological model, they can infer what the expansion rate today should be. This is not a direct stopwatch placed beside a nearby galaxy. It is a prediction carried forward from the oldest observable light, through a model of cosmic ingredients and evolution, into the present. This is the early universe route. It is built from afterglow and inference. The unsettling thing is that both routes are powerful, both have been refined, both have been checked, and yet the values have not settled into perfect agreement. A telescope mirror opens above Earth. A detector receives light from a pulsing star in a distant galaxy. Another instrument maps microwave variations across the whole sky, old, cold patterns left from a time before stars. These are not the same kind of evidence. They do not fail in the same way. That is why their disagreement matters. If one method were obviously weak, the story would be simple. It is not simple. The local measurements tend to give a higher expansion rate. The early universe prediction, using the standard model, gives a lower one. The difference is not enormous in everyday language, but cosmology is not everyday language. A few kilometers per second per megaparsec can become a question about whether the model is missing something, whether the distance ladder still contains a hidden systematic error, or whether the early universe carried an ingredient not yet understood. This is why the Hubble tension belongs in the same emotional family as dark matter and dark energy. It is not merely another number in dispute. It is a sign that the universe may be resisting closure at the level of its basic accounting. Dark matter says the visible mass is not enough. Dark energy says expansion is not behaving the way simple gravity once suggested. The Hubble tension says that even after those dark ingredients are included in a successful model, the route from the young universe to the present may still contain a mismatch. The ruler does not quite meet itself. That phrase is easy to misunderstand. The universe is not falling apart because of the Hubble tension. Galaxies do not care whether human equations are uneasy. Stars continue burning. Space continues expanding. What breaks is not reality. What breaks is the feeling that the story is almost finished. For a while, the standard cosmological model has been astonishingly good. With a small set of ingredients, it explains the microwave background, the abundance of light elements, galaxy clustering, large-scale structure, and accelerated expansion. It is not a fragile guess. It is one of the great achievements of modern science. That is exactly why the tension hurts. A weak model can fail without surprise. A strong model leaves a cleaner wound when it fails at the edges. The stronger the structure, the more meaningful the crack. There are possible ordinary explanations. Maybe the local distance ladder still hides a bias. Maybe Cepheid calibration, dust, stellar crowding, supernova environments or selection effects have not been fully tamed. Maybe part of the early universe inference depends on assumptions that should be adjusted. Maybe different measurement methods will eventually converge as data improve. Science must leave that door open. But there is another possibility. The tension may be a symptom of new physics. That phrase should be used softly. New physics is not a magic drawer where every disagreement is thrown. It is earned only when ordinary explanations begin to lose their grip. If the Hubble tension remains under stronger data, it could point toward changes in the early expansion history, extra relativistic particles, evolving dark energy, modified gravity, or some other adjustment. Each possibility has a cost. Change the early universe, and the microwave background must still fit. Change dark energy, and structure growth must still fit. Change gravity, and lensing, galaxies, clusters, and local tests must still survive. The universe is not a loose collection of mysteries, it is a locked system of consequences. Tug one thread, and the whole web answers. That is why the tension is so dangerous to easy storytelling. It cannot honestly be turned into scientists know nothing. They know too much for that. It also cannot honestly be flattened into just an error, because the disagreement has persisted through serious scrutiny. The honest story is more uncomfortable. Scientists may be looking at a mismatch between two high-quality ways of reading cosmic history, and no one yet knows whether the flaw is in the ruler, the model, or the universe's hidden ingredients. This is the midpoint where the original secret changes shape. At first, the problem seemed to be invisible mass. Then it widened into accelerating emptiness. Now the problem becomes the act of measurement itself. Not because measurement is hopeless, but because measurement has become precise enough to expose disagreements that rougher tools would have hidden. Crudeness can create false mysteries. Precision can create real ones. We can still measure the ancient afterglow. We can still observe distant supernovae. We can still calibrate stars, map galaxies, compare models, and run the same question through different machines. The universe is still legible. But the handwriting has begun to disagree with itself. A human being wants a ruler to be innocent. A ruler should measure without drama. But the cosmic ruler is built from exploding stars, ancient radiation, stellar pulsations, dust corrections, gravitational assumptions, and the expansion of space itself. It is not a simple object. It is an argument made carefully enough to become a number. And when two careful arguments return different numbers, the darkness deepens in a new direction. Not toward an object hidden in a halo, not toward an energy hidden in the vacuum, toward the possibility that the bridge between the early universe and the present universe is missing a plank we have not yet learned how to see. The secret may not only be what the universe contains, it may be how the universe keeps time. The mystery did not survive because the instruments were vague. It survived after the instruments became almost brutally precise. That is the part that changes the emotional shape of the story. A weak telescope can leave room for monsters. A poor measurement can make ignorance look larger than it is. But modern cosmology has not been built from blurry wonder. It has been built from machines that take the sky apart with an almost inhuman patience. A mirror opens in orbit. A detector cools itself against its own heat. A spacecraft stares at darkness until ancient photons become statistics. On a mountain, a telescope gathers light that began its journey before mammals had names. Underground, a detector waits for an event so small that a stray background particle can impersonate the truth. The universe is not being guessed at casually. It is being cornered. And yet the center still does not open. Consider the strange position of the cosmic microwave background. It is faint, cold, and nearly uniform, but it is one of the strongest pieces of evidence human beings possess about the early universe. Missions that mapped it did not merely produce an image, they produced a constraint system. Tiny variations in temperature became measurements of density, geometry, matter content, and the seeds of structure. The map is not dramatic in the way a galaxy photograph is dramatic. It has no spiral arms, no glowing nebula, no obvious place for the eye to rest. It looks almost like a coded skin stretched over the whole sky. But inside that mottled pattern is an astonishing claim. The early universe can be measured so carefully that a model can predict what kind of cosmos should grow from it. That is why the Hubble tension matters so much. The ancient map works too well to ignore. The nearby measurements work too carefully to dismiss. A cruder age would have missed the disagreement. A less disciplined age might have turned it into mythology. Modern science does something stranger. It holds the disagreement in public, under pressure, without allowing either side to become a story too quickly. Then comes Hubble, the telescope whose name almost became synonymous with cosmic distance. Above the blur of Earth's atmosphere, it watched Cepheid variable stars in distant galaxies, helped calibrate the distance ladder, and deepened the reach of supernova measurements. Its images also changed public imagination, but its quieter work mattered just as much, turning faint periodic changes in stars into rungs on the largest ruler ever built. A Cepheid is not just a star that brightens and dims. It is a clock with a luminosity relation. When its pulse is measured, and its apparent brightness is compared to what its true brightness should be, distance begins to emerge. The process is delicate. Dust can interfere. Crowded stellar fields can confuse the signal. Metal content can matter. Every correction is a place where error can hide. So the measurements are checked, extended, revised. Then Webb enters, not as a replacement for every older answer, but as another eye with different strengths. Its infrared vision can pierce dust more effectively and inspect some of the same distance indicators with sharper detail. When Webb helps examine the local distance ladder, the hope is not simply to confirm a preferred answer. The hope is to find whether the old ruler was warped by something subtle. That is what makes the persistence of the puzzle uncomfortable. Better instruments do not always remove mystery. Sometimes they remove excuses. The same thing is happening across the dark universe. Euclid was built to map billions of galaxies across cosmic time, measuring shapes, distances, clustering, and weak gravitational lensing. Its purpose is not to take pretty pictures of the unknown. It is to watch how structure grew and how expansion changed, so dark matter, dark energy, and gravity can be tested against an enormous statistical map. Weak lensing is almost cruel in its subtlety. Individual galaxy shapes are messy. Galaxies are not born as perfect circles waiting to be distorted, but across millions and billions of them, tiny alignments can reveal how intervening mass has bent their light. The signal is not a shout. It is a bias in the crowd, a whisper that becomes meaningful only when the universe is counted at scale. This is the new kind of astronomy. Not one heroic image. A disciplined accumulation of almost invisible effects. Planck mapped the old fire, Hubble built rungs in distance, Webb sharpened part of the local ladder. Euclid maps the dark scaffolding and expansion history. Other surveys measure baryon acoustic oscillations, the fossil spacing left by sound waves in the young universe. Rubin will repeatedly scan the changing sky, catching transient events and mapping structure with unprecedented depth. Roman is designed to probe cosmic acceleration through wide-field infrared surveys, supernovae, and weak lensing. Each instrument enters with its own personality. One listens to the afterglow, one measures candles, one traces distortions, one counts galaxies, one waits for explosions, one watches the sky change with time. Together they form something larger than a collection of machines. They form a cross-examination. That is why easy answers keep failing. If dark energy changes over time, it must fit supernovae, lensing, clustering, and the microwave background. If gravity is modified, it must still work where general relativity has been tested with exquisite care. If dark matter is not a particle but a misunderstanding, the alternative must explain galaxy rotation, cluster collisions, lensing maps, structure growth, and early universe patterns without breaking something else. The unknown is not free. It is trapped inside evidence. That is the difference between mystery and fantasy. Fantasy can choose a shape because the story wants it. A scientific mystery must survive every measurement that should have killed it. Dark matter has survived because the gravitational need keeps appearing. Dark energy has survived because acceleration keeps appearing. The Hubble tension has survived because the mismatch has not yet collapsed under stronger scrutiny. But survival is not identity. The measurements say there is something there, or something wrong, or something incomplete. They do not yet say what the final language should be. There is a soft machine sound in that uncertainty. Servers cooling, mirrors adjusting, reaction wheels turning, a shutter opening, a radio signal arriving from a spacecraft that has already done its work in silence. The universe is being reduced to numbers, and the numbers are refusing to become simple. That refusal is not a failure of science. It is the reason science remains alive. A completed universe would be easier to narrate. Ordinary matter, dark energy, expansion rate, final fate. Every term nailed down, every number closing neatly over the unknown. But the real universe is less obedient. It lets us measure enough to build confidence, then leaves a gap exactly where confidence wants to become possession. This is the edge of certainty. Not the edge where knowledge ends and nonsense begins, but the edge where knowledge is sharp enough to cut itself. Every new instrument narrows the hiding places. Every survey makes the allowable answers smaller. The unknown becomes less cinematic, less flexible, less available to myth. But it also becomes harder to escape, because it is no longer a shadow at the edge of the fire. It is inside the best map. It is inside the best ruler. It is inside the difference between what the universe shows and what the equations still cannot name. There is one question that waits behind almost every dark matter argument, patient and uncomfortable. What if the missing thing is not a thing? What if the error is not in the inventory of the universe, but in the rule used to weigh it? That possibility cannot be waved away. Gravity is not a minor detail here. Gravity is the language through which most of the evidence arrives. Galaxy rotation, lensing, structure growth, expansion history, the microwave background interpreted through a model. Again and again, the universe is being read through gravity. So a reasonable mind has to ask whether the unseen mass is truly unseen mass, or whether gravity itself changes its behaviour across scales larger than the ones where it has been tested most directly. This is the doorway into modified gravity. It is not a single answer. It is a family of attempts to explain cosmic behaviour by adjusting the gravitational law, or by extending general relativity, rather than adding a new form of matter. Some versions try to account for galaxy rotation without dark matter. Some try to explain cosmic acceleration without dark energy. Some work in narrow places and strain in wider ones. Some solve one class of observations, then fail when the whole sky is allowed to speak. That last phrase matters. The whole sky is not one test. It is many tests pretending to be one universe. A theory that helps with spiral galaxies must also face clusters. It must face gravitational lensing. It must face cluster collisions where ordinary gas and inferred mass appear separated. It must face the cosmic microwave background, the growth of structure, the way galaxies cluster, the way light bends, the way expansion changes with time. It must not only repair one crack, it must keep the building standing. This is why dark matter remains so hard to replace. Not because scientists are emotionally attached to invisible particles, not because the standard model of cosmology is sacred, but because the missing mass interpretation has become woven through many independent observations. Remove it, and the universe does not simply become cleaner, it loses a load-bearing beam in several rooms at once. Still, the question keeps its force. Gravity is already stranger than instinct. Newton made it look clean enough to feel inevitable. Masses attract, planets orbit, apples fall. Einstein made it deeper and less intuitive. Matter and energy curve space-time, and objects follow that curvature. Gravity stopped being a force in the old simple sense and became geometry, a change in the stage itself. If gravity has already changed once in human understanding, why assume the last version is final? That question is honest. It is also dangerous when made too easy. General relativity is not a fragile antique. It has survived severe tests. Planetary orbits, gravitational redshift, light bending, pulsars, gravitational waves, black hole imaging, and timing corrections that make satellite navigation possible. Any deeper theory cannot simply discard it like an old myth. It has to reproduce its successes, then explain where and why it differs. A new gravity must be both revolutionary and obedient. That is a narrow target. The appeal of modified gravity is obvious. It would turn the terrifying secret into a failure of interpretation rather than a hidden cosmic substance. The universe would not be filled with an undetected particle population. Instead, our equations would be incomplete across the largest and weakest gravitational regimes. The invisible scaffolding would be partly an artifact of using the wrong law at the wrong scale. There is a strange relief in that thought. And then the relief begins to collapse under the evidence. Because galaxies are not the only problem. Lensing still asks how light knows where to bend. Clusters still ask why mass maps and ordinary gas do not always sit together. The early universe still asks why its acoustic pattern looks the way it does. Structure formation still asks how matter gathered fast enough, in the right pattern, across time. Some modified gravity ideas can handle some of this. Few handle all of it naturally. That does not make them worthless. They force cosmology to ask which assumptions are truly necessary. They expose where dark matter models are strong and where they are only convenient. They keep the field from confusing a successful framework with final truth. But they also show how expensive it is to replace an unknown. A scientist can remove dark matter from a model and feel, for a moment, that the universe has become less haunted. Then the equations demand compensation elsewhere. The gravity law changes. Extra fields appear. New parameters are added. The clean room fills with machinery. The ghost has not vanished. It has moved into the walls. The same is true for dark energy. Perhaps cosmic acceleration is not driven by a vacuum energy or a new field. Perhaps general relativity fails subtly at the largest scales. Perhaps the geometry of the universe, when averaged across cosmic structure, has been misunderstood. Perhaps gravity weakens, leaks, evolves, or behaves differently when the distances become almost impossible. Each idea is allowed to knock, but it must bring evidence. A theory of altered gravity must explain why expansion accelerates while preserving the microwave background fit, the growth of structure, local gravity tests, gravitational wave constraints, and the observed behavior of galaxies and clusters. The difficulty is not inventing a mathematical possibility. The difficulty is surviving contact with everything already known. This is where the universe becomes a locked room. There are many keys that open one drawer. Very few open the door. A dark observatory measures faint galaxies. A satellite maps an ancient glow. A detector catches ripples in space-time from distant mergers. A supernova fades in a galaxy that was old before Earth grew forests. Each measurement is a witness. The final theory has to understand them all. That is why the question is no longer simply whether scientists can explain the dark universe. The question is what kind of explanation the universe will permit. A particle explanation would mean the cosmos contains a dominant form of matter outside the known luminous family. A modified gravity explanation would mean the rules of attraction themselves are incomplete across cosmic scales. A dark energy field would mean empty space carries a hidden dynamical ingredient. A cosmological constant would mean the vacuum has a stubborn, fate-shaping property no one yet understands. Every door leads to something unsettling. There is no version where the universe returns to common sense. This may be the deepest trap in the title. The phrase "scientists cannot explain" sounds as if explanation is waiting just beyond one missing fact. Find the particle, fix the equation, measure the rate, name the field, then the secret will end. But the history of gravity warns against that hope. When explanation arrives, it may not make the universe feel more familiar. Newton explained the falling apple by tying it to the moon. Einstein explained gravity by removing the familiar idea of force and replacing it with curved spacetime. A future explanation may solve the equations by making reality stranger, not simpler. Science does not promise to restore intuition. It promises to discipline astonishment. So if gravity is not the whole story, the universe is not less mysterious. It is more precisely mysterious. The hidden mass may still be there. The hidden energy may still be there. Or the laws that made both seem necessary may be incomplete in a way that only becomes visible when the cosmos is treated as a single experiment. Either way, the visible world remains suspended inside something deeper than appearance. A star moves. Light bends. Space expands. The ruler disagrees with itself. And somewhere beneath those facts, unseen ingredients or unfinished laws are doing work that matter can only detect after the work is done. The future of the universe is difficult to fear because it does not arrive like a disaster. It does not come as one impact, one flame, one final sky. It comes as a change in permission, a little less contact, a little less warmth, a little less shared light between regions that once belonged to the same visible story. Dark energy, if it continues behaving the way the simplest model suggests, writes that future quietly. Not by tearing galaxies apart today, not by pulling Earth away from the sun, not by making the stars vanish. Bound systems remain bound where gravity is strong enough to hold them. The solar system does not expand with the universe. The Milky Way does not lose its stars because space is growing between them like an inflating room. That is not where the danger lives. The danger lives between the unbound things, between galaxy groups, between clusters, across the great distances where gravity has not gathered matter into one local family. On those scales, expansion is not background scenery. It is the motion of the stage itself, and dark energy appears to be making that motion accelerate. This is a fate written not in collision, but in separation. The body understands collision. It understands heat, pressure, impact, the nearness of harm. Separation is harder to fear because it can look peaceful. Two lights in the distance, then one light a little dimmer, then redder, then weaker, then gone, not because it died, but because the universe placed too much expanding distance between the light and the observer. There is no scream in that. Only loss of address. Imagine a signal leaving a galaxy so distant that the expansion of space is already working against it. The photons travel at light speed, the fastest speed information can travel through space. Nothing local outruns them, yet on cosmic scales, the distance they must cross can grow so fast that the signal never arrives. The light is moving correctly, the universe is expanding more decisively. That is one of the coldest ideas in cosmology. A message can be real and still never reach you. A galaxy can exist and still never enter your future sky. This does not mean every distant object disappears at once, or that the present night is about to empty itself. The process is immense, slow, and model-dependent. But the direction matters. If accelerated expansion persists, the far future becomes more isolated. The visible universe shrinks in a practical sense, not because reality becomes smaller, but because access becomes poorer. Existence remains. Contact fails. The older universe would become an archive, with doors closing. Distant galaxies whose light reaches us now may eventually cross horizons of observability. Their old photons can still arrive for a time, stretched thinner and colder by expansion. Their images can remain in records, their positions can be modelled, but future light, newer light, light that would have told later chapters of their history, may never reach this region of space. A telescope in that future would not simply be looking farther. It would be looking after a disappearance. There is a strange mercy in our timing. We live while the cosmic microwave background is still measurable, while galaxies beyond the local group still populate the sky, while large-scale structure can still be inferred from surveys, while the expansion history can still be reconstructed from many witnesses. The universe has not hidden all its evidence from us yet. That yet is not panic. It is perspective. Science often sounds like pure intelligence, as if knowledge depends only on minds becoming clever enough. But cosmology shows that knowledge also depends on being born during an era when the evidence is available. A civilization can be brilliant and still arrive too late for certain clues. It can build exquisite instruments under a poorer sky. A far future astronomer inside a merged local galaxy, after other galaxies have faded beyond reach, might inherit a universe that looks lonelier than ours. The local stars would remain. Stellar evolution would continue. Some remnants would cool. New stars would eventually become rarer as gas is exhausted. but the grand external evidence for the wider cosmic web could be harder to recover. The universe would not be less vast. It would be less legible. That distinction is devastating because it turns cosmic fate into an epistemological loss. Not only do things move apart, the proof that they were ever together becomes harder to keep. The sky becomes less like a window and more like a memory. Dark energy is therefore tied to the fate of knowledge itself. If the simplest picture holds, the very expansion that helped reveal cosmic history to us will one day conceal much of that history from later observers. The universe can erase not by destroying objects, but by stretching the connections that made them observable. This is not the dramatic end people often imagine. No final explosion, no curtain of fire, no sudden judgment written across the stars. The more likely long future, under persistent acceleration, is colder and more patient. Galaxies outside the bound neighbourhood recede from meaningful contact. Star formation slows as gas is used up. Existing stars age, brighten, collapse, fade, or leave remnants. White dwarfs cool. Neutron stars and black holes remain as severe relics. The universe becomes less luminous, less connected, less generous with usable energy gradients. Life, if it exists elsewhere, would not confront a single wall. It would confront a thinning of possibility. That is the bodily translation of cosmic acceleration. Imagine not dying from a wound, but waking each year to find one more road gone, one more harbour unreachable, one more language no longer capable of sending a reply. The house is still standing, the lamp still works, but the world around it has withdrawn. On cosmic timescales, expansion is a withdrawal of the unbound. The future, written by dark energy, does not make ordinary matter meaningless. If anything, it makes ordinary matter more fragile and precious. Every star is a temporary furnace in a universe whose large-scale trend is toward colder separation. Every planet with chemistry is a local exception. Every living body is a brief arrangement of warmth, pressure, memory, and repair inside a cosmos that, on its widest scales, does not gather forever. The visible universe becomes an event, not a possession. For a while, matter clumps, stars ignite, galaxies shine, heavy elements form, worlds cool into chemistry, eyes open under atmospheres, telescopes rise out of one planet's crust and catch ancient light before it becomes too faint, too red, too removed. For a while, the universe can know itself. That may be the quietest consequence of dark energy. It does not only shape how far galaxies move, it changes the emotional status of the present. We are not observing the universe from a permanent platform. We are observing during a luminous interval, after structure formed and before the widest evidence becomes unreachable. The night sky is not merely a view. It is a temporary privilege. And if dark matter taught us that the bright world rests inside hidden gravity, dark energy teaches that the bright world also rests inside limited time. Not the small time of a lifespan, though that is real enough. The larger time of observability itself. The era in which the universe can still send enough of its own history across the dark to be understood. The fate written in the unknown is not just cooling. It is not just distance. It is the slow conversion of a shared cosmos into islands of local memory, each surrounded by an expansion too large to cross. A galaxy still glows. A photon still leaves. But somewhere ahead, the road between leaving and arriving becomes longer than the future allows. By the time the story reaches ordinary matter, it should feel smaller than it did at the beginning. Not less miraculous. Smaller. Because ordinary matter is the part of the universe that makes itself easy to love. It burns in stars. It condenses into planets. It becomes oceans, minerals, atmospheres, cells, forests, bones, language, memory. It makes every object that can bruise a hand or warm a room. It is the matter that can be photographed, mined, breathed, buried, eaten, and turned into instruments that look back at the sky. It is the matter that became us. And it is not the main ingredient. That sentence is easy to say, but difficult to let into the body. Almost everything that has ever mattered to human history belongs to a cosmic minority. Every empire, every city, every machine, every famine, every written law, every burned library, every fossil, every grave, every child asleep under a roof. All of it belongs to the visible fraction. The rare fraction. The part that shines, or once shone. The part that interacts richly enough to become complex. This is not a humiliation of life. It is a correction of scale. The atoms in a human body are not trivial because they are rare. Rarity does not mean insignificance, but it does mean the universe is not built around what we are made of. That is the wound ordinary matter carries. It can become conscious, but not central. The cosmic inventory, in the Standard Model, places ordinary atoms in a small slice of the whole budget. Dark matter is much larger. Dark energy is larger still. The numbers are model-dependent, refined by observations, vulnerable to future sharpening. But the broad picture is stable enough to disturb. The stuff of stars and bodies is only a few % of the total cosmic accounting. A few %. That is a devastating phrase when it contains every face ever born. The body wants to reject it because the body's world is made entirely from that few %. A stone in the hand feels complete. A tree in the wind feels undeniable. Blood on a fingertip, dust on a windowsill, rain against a roof, the smell of metal, bread, smoke, sea salt. Ordinary matter fills the senses so thoroughly that it feels like the definition of reality. It is only locally dominant. Cosmically, it is an exception with texture. This is one reason the dark universe is not merely a scientific puzzle. It is a philosophical injury delivered by measurement. Copernicus moved Earth from the centre. Darwin placed humanity inside animal history. Geology buried human time under deep time. Astronomy expanded the scale until the Milky Way became one galaxy among multitudes. And now cosmology does something quieter, but just as severe. It tells the material self that even its substance is not the main substance. The correction is not spatial now, it is compositional. We are not only not central in location, we are not made of the dominant stuff. There is a soft horror in that, but also a strange reversal. The same ordinary matter that is cosmically minor is capable of complexity precisely because it does interact. Atoms exchange energy, electrons form bonds, light couples to matter, molecules assemble and break, chemistry becomes metabolism, metabolism becomes sensation, sensation becomes memory. Memory becomes a mind capable of asking what the invisible majority is doing. Dark matter may dominate mass on large scales, but it does not make tables, skin, oceans, or questions in any familiar way. Its silence is part of its power. Ordinary matter's noisiness is part of its gift. A hydrogen atom can absorb light. Carbon can form chains. Oxygen can bind and release. Iron can sit in blood and rust in rain. These interactions make ordinary matter detectable, but they also make it fertile. The same electromagnetic richness that allows telescopes to see stars also allows nervous systems to exist. The visible fraction is small because it is not the only cosmic actor. But it is vivid because it can touch itself into complexity. Imagine the universe as a vast, dark ocean where most of the mass and fate belong to currents you cannot see directly. On the surface, here and there, foam catches starlight. The foam is not the ocean, and it does not steer the deepest currents, but for a moment it shapes itself into patterns delicate enough to notice the sea. That is ordinary matter. Foam that learned mathematics. The image is imperfect, as all images are at this scale, but it points toward the emotional truth. We are not the ocean. We are a brief, luminous complication on its surface, carried by currents older and larger than our categories. And yet the complication matters because it can bear witness. A rock does not know that it belongs to a rare category. A star does not know that its light is a visible trace of a minority ingredient. A galaxy does not know that its spiral arms are suspended in a dark halo. But a small nervous system on a small planet can build the idea of a halo. It can measure lensing. It can map the microwave afterglow. It can compare two values of the Hubble constant and feel the wound of disagreement. The universe produced, from its minor ingredient, a thing that can notice the majority. There is no need to make that mystical. It is already strange enough. The rare fraction built the question. The larger fraction may hold the answer. This should change how the night sky feels, not because the stars are less beautiful, but because their beauty is now understood as partial testimony. The glow is not false, it is incomplete. Each star is a furnace inside the minority. Each planet is a local condensation of the exceptional. Each body is a temporary arrangement of atoms that belong to the small, visible family. The ordinary matter in us was forged through real histories: early nucleosynthesis, stellar burning, supernovae, neutron star mergers, planetary accretion, geochemistry, biological selection, cultural memory. The path from hydrogen to a listening mind is not simple. But the miracle becomes more exact when placed against the dark. It is not the miracle of being central. It is the miracle of being possible. A universe dominated by invisible mass and accelerating emptiness still allowed a thin minority of matter to cool, clump, ignite, recycle, and organize. It allowed heavy elements to form in stars and explosions. It allowed planets to hold atmospheres. It allowed liquid water somewhere long enough. It allowed chemistry to become restless under energy flow. That permission may be temporary. It may be local. It may never have been guaranteed. The atoms in a hand feel solid because the scale is forgiving. But those atoms belong to a universe where most of the budget is elsewhere, where the future may be governed by expansion, where the largest structures were guided by invisible gravity, where the bright era itself is finite. A hand raised under the stars is not a symbol of mastery. It is a small visible event inside a mostly invisible cosmos. The secret of the universe, if the title can still use that word, is not that humanity is meaningless. It is that meaning is made from the minority material. Everything we call meaning has been assembled from the part that is not in charge. That does not empty meaning. It sharpens it. Because if ordinary matter is rare, interactive, luminous, temporary, and capable of knowing its own incompleteness, then the bright fraction is not merely a decorative edge on the dark universe. It is the place where the universe becomes troubled by itself. The visible part asks. The invisible part answers only through consequences. And between the two, every act of science becomes a negotiation between the smallness of our substance and the reach of our attention. Science has a strange talent for making the invisible more real than the visible. That sounds impossible at first. Visibility feels like proof. A thing appears, reflects light, takes shape in the eye, and the mind relaxes. There it is. A planet, a star, a galaxy, a line on a screen. The world enters through the senses and becomes trustworthy because it has given itself an outline. But much of the universe has never worked that way. The deepest knowledge often begins when sight fails and something else remains. A planet is known by the tug it gives another planet. A black hole is known by the orbiting stars around it, by hot gas near its edge, by gravitational waves from mergers, by the darkness it carves into surrounding light. An atmosphere is known by the colours removed from starlight passing through it. A distant world is known by the slight dimming of its star. The universe is full of things learned from their consequences. Dark matter and dark energy are not exceptions to that method. They are the extreme version of it. This is where the fear changes again. The frightening part is not that science can know nothing without direct sight. The frightening part is that science can know a great deal without being allowed to touch the thing itself. It can build a cage of evidence around an absence. It can measure the absence from several directions. It can give the absence a mass budget, a gravitational role, a place in the early universe, a function in structure formation, and still not know its identity. That is a more adult kind of ignorance. Not empty. Earned. A child's ignorance is a blank wall. A scientist's ignorance, at its best, is a wall covered with measurements showing exactly where the door should be. This is why saying scientists cannot explain the universe is both too crude and not crude enough. It is too crude because scientists explain an astonishing amount. They can trace nuclear reactions in stars. They can model the cooling of the early cosmos. They can calculate the bending of light, measure redshift, map galaxy clustering, predict the abundance of light elements, and use gravity as a language across billions of years. But the phrase is not entirely wrong. At the deepest level, the dominant components remain unidentified. The central terms in the cosmic ledger still point to unknown physical meanings. Dark matter behaves like mass, but has not been caught as a known particle. Dark energy behaves like a driver of accelerated expansion, but may be a cosmological constant, a field, modified gravity, or something that current categories have not yet made clean. The explanation is powerful. The ontology is unfinished. That distinction matters. A map can be useful before the land is fully understood. Sailors crossed oceans with imperfect maps. Doctors treated symptoms before microbes were known. Engineers used electricity before electrons were part of ordinary speech. Knowledge often works before it becomes complete. Cosmology is doing something like that with the whole universe. It can say where the hidden gravity must be distributed for galaxies and clusters to make sense. It can say how much dark energy seems required for expansion history to fit. It can say what the microwave background permits and forbids. It can say which simple explanations have failed. But it cannot yet say, in the deepest physical language, what most of the cosmic budget is. There is a quiet dignity in admitting that. A weaker culture would turn the gap into conspiracy. A louder one would fill it with supernatural certainty or cheap dread. But the honest version is harder and more beautiful. We have measured the edge of our comprehension with tools made from the small, visible fraction. The tools are good enough to reveal that the unseen majority is not optional. They are not yet good enough to make it familiar. The universe has become partially transparent to mathematics and partially opaque to meaning. That opacity is not a defeat. It is the condition under which the next science is born. In a late-night control room, a researcher looks at a screen full of residuals, tiny deviations, error bars, model fits, a number that should agree with another number, but does not. There is no dramatic music in the room, only ventilation, keyboard taps, a cooling fan. Yet the pressure is real, because those small differences may decide whether the problem is hidden matter, hidden energy, altered gravity, or an unnoticed flaw in the measurement ladder. The cosmos does not need to shout to threaten a worldview. Sometimes it only needs to be inconsistent in the 6th decimal place. This is the discipline that separates science from myth. Myth can make the darkness speak immediately. Science must wait until the darkness leaves a trace. It must ask what the trace could mean. What else could imitate it? What measurement would separate one answer from another? What error could still be hiding inside the instrument? That patience is not cold. It is respect. The universe is under no obligation to be understood quickly, and human beings have done their best work when they have stopped demanding that it behave like a story written for them. The irony is that this restraint creates a deeper wonder than exaggeration ever could. A false claim burns hot and then collapses. A careful uncertainty can last for generations. It can build observatories. It can send spacecraft into cold orbits. It can lower detectors underground. It can train thousands of minds to spend their lives narrowing a silence. The silence becomes a shared object. Not because everyone agrees on the answer, but because the question has become exact enough to inherit. This is what science can know without seeing. It can know that something is missing from the visible inventory. It can know that the missing part has consequences. It can know that those consequences appear in motion, lensing, clustering, background radiation, and expansion. It can know that some explanations fail. It can know that future answers must pass through the evidence already gathered. It can know the shape of the lock before it has the key. That may be the most human position in the universe. We are not blind, but we are not sovereign. We can infer farther than we can touch. We can build meaning from traces. We can admit uncertainty without surrendering precision. A footprint is not the animal. A bent beam is not the mass. A redshift is not the whole history of expansion. A fluctuation in the microwave sky is not the first instant of time. But each is a contact point between the visible and the hidden. Enough contact points become a map. Not a final map. A living one. And this is why the dark universe should not be reduced to a slogan about fear. Its real force is subtler. It shows that the universe can be deeply intelligible and deeply withheld at the same time. It can allow equations to work while refusing to make the nouns behind those equations simple. It can give us a structure, a history, a fate, and still hide the substance of the structure, the engine of the fate, and perhaps the rule underneath the history. The eye looks for light. The mind follows consequence. And somewhere beyond the reach of direct touch, the universe keeps answering in the only language it has offered so far: motion, curvature, expansion, and the stubborn shape of what must be there. The night sky has changed, but nothing in it has moved. That is the final cruelty of understanding. The same stars remain. The same pale band of the Milky Way crosses the dark, if the air is clean enough. The same planets wander along their old paths. A telescope still finds galaxies suspended like tiny embers in a field so black it seems almost merciful. But after the dark universe enters the mind, the sky no longer looks like the whole thing. It looks like leakage, a visible trace from a larger reality that does not need to shine in order to govern. The stars become not the main text, but illuminated fragments inside a deeper manuscript. Galaxies become bright punctuation marks in an invisible grammar. Empty space stops feeling empty. Darkness stops feeling like absence. The universe behind the universe has stepped forward, not as an image, but as a demand. This is the part no photograph can hold. A photograph gives the eye what the eye wants: shape, colour, glow, scale made beautiful. It can show a spiral galaxy with blue arms and a golden centre. It can show a cluster full of old red galaxies crossed by distorted arcs from more distant light. It can show the mottled microwave afterglow, the oldest visible surface we can reach. But it cannot show the unease connecting them. It cannot show the missing mass as a substance. It cannot show dark energy as a hand widening the spaces between unbound galaxies. It cannot show the Hubble tension as a wound in a ruler built from stars and ancient radiation. It cannot show why ordinary matter, for all its brilliance, is only a small visible flare inside a much larger accounting. That work belongs to inference. And inference is one of the strangest powers consciousness has ever produced. From inside a body made of ordinary atoms, on a planet orbiting an ordinary star, in a galaxy held partly by something unseen, human beings have learned to read absence with enough discipline that absence becomes evidence. A star moves too quickly. Light bends too strongly. The microwave sky ripples in a particular pattern. Distant supernovae look too dim for an older expectation. The expansion rate refuses perfect agreement across cosmic time. No single clue owns the secret. The secret lives in the convergence. It is tempting, at the end, to turn that convergence into a final answer, because endings like closure. A good story wants the hidden thing named. It wants the locked room opened, the shadow stepped into light, the universe made honest after a long refusal. But the universe has not offered that ending. Not yet. It has offered something more difficult, a working model with unknown foundations, a map that functions while its deepest materials remain unnamed, a cosmic history whose visible chapters are supported by invisible scaffolding and pushed toward an uncertain fate by a component no one has touched. There is no honest way to make that small. Dark matter may be a particle or family of particles still beyond detection. Dark energy may be the cosmological constant, or something dynamic, or a sign that the theory itself is incomplete at the largest scales. The Hubble tension may soften under better measurements, or it may harden into evidence that the standard picture needs another ingredient. Modified gravity may solve part of the riddle, or fail under the combined weight of lensing, clusters, structure, and the ancient afterglow. Every possibility leaves the universe strange. That is the real answer beneath the title. The terror is not that scientists cannot explain anything. They can explain enough to make the darkness precise. The terror is that the explanations, when taken seriously, do not return us to a familiar cosmos. They lead to a universe in which light is partial, matter is mostly unseen, emptiness may have consequence, and the future of visibility itself may be temporary. A smaller mind would prefer a cleaner fear. A monster at the edge, a signal from beyond, a hidden object approaching Earth, something with a face, a direction, a countdown. The actual fear is more patient. It says that the conditions making knowledge possible are thin. It says that the matter making bodies possible is rare. It says that the sky has always been a selective witness, showing only the fraction of reality that knows how to glow. It says that a civilization can spend centuries improving its instruments and still arrive at a border where the nouns fail before the equations do. There is a strange humility in that border. Not defeat, humility. The kind that does not ask us to stop knowing, but to stop confusing visibility with totality. The kind that makes a starry night feel less like a ceiling and more like a set of exposed nerves on the surface of something too large to display itself directly. The Milky Way, then, is not just a river of stars. It is a bright seam in a dark halo. A galaxy cluster is not just a city of galaxies. It is a mass field where light from behind is bent into testimony. The cosmic microwave background is not just ancient radiation. It is the cooled skin of a young universe carrying the imprint of ingredients still unnamed. And empty space is not simply the place where nothing happens. It may be where the future is being decided. This does not make the universe cruel. Cruelty implies intention, and nothing in the evidence requires that. The universe is not hiding because it wants to humiliate us. It is not silent because it is withholding mercy. It is simply larger than the habits of creatures raised among solid things, warm light, short distances, and causes that can be touched. We are the ones who expected reality to present itself in human terms. The cosmos did not agree. Yet there is tenderness in the fact that any of this can be known at all. Against all scale, against all lateness, against all the weakness of ordinary matter, something here learned to build mirrors for starlight, detectors for microwaves, chambers for rare collisions, equations for curvature, surveys for galaxies, and stories careful enough not to lie about what remains unknown. The rare fraction became attentive. That may be as close to central as ordinary matter ever gets. Not because it dominates the universe, but because, for a brief interval, it can notice that it does not. It can look at the bright sky and understand that brightness is not the same as truth. It can feel the old comfort break, then build a better form of wonder from the pieces. A final image remains. A person standing under the night, hearing only wind, insects, maybe the faint electric hum of a town behind them. Above them, stars appear fixed and clean. The Milky Way is a pale wound across the dark. Nothing announces the hidden mass. Nothing announces the accelerating future. Nothing in the body feels the cosmic microwave background passing through the instruments that were built to hear it. The sky seems quiet, but the quiet is crowded with consequences. Light from ancient galaxies crosses invisible wells. Space between unbound islands stretches toward a colder privacy. The old afterglow thins across every direction. Ordinary atoms, gathered for a moment into eyes and memory, look upward from inside the minority and try to understand the majority that does not shine back. The secret was never that the universe is dark. The secret is that the darkness is not empty. And the light, beautiful as it is, was never the whole universe speaking.